Mm-hmm.
So we can start, and I have a pleasure to propose and talk with Rogozinnikov about Hermitian Lie groups and their interpretation as symplectic groups over non-commutative algebras. Jenny, please.
Yeah, thank you very much. And first of all, I would like to thank the organizers to give me this opportunity to speak in the seminar. And right, I am going to talk today about Hermitian Lie groups. And this is a joint work with Daniele Alessandrini, Arkady Berenstein, Vladimir Retakh, and Anna Wienhard. And here is our plan for today. So first of all, I will introduce Hermitian symmetric spaces and Hermitian Lie groups. Then we will discuss some examples that actually motivated our research. Then I will give you a definition what is a symplectic group or algebras and what condition do we need to assume for these algebras to realize Hermitian Lie groups. And finally, I will talk about models of symmetric spaces. I hope I managed to do everything. So actually, what how much time do I have? Exactly 1 hour or 50?
1 hour, but as you want.
Okay, excellent.
1 hour is an option.
Okay, so it's not like usual 50 minutes. Okay, excellent. So Hermitian Lie groups is a very interesting class of semi-simple Lie groups. They have particularly nice properties from different points of view. On one hand, their symmetric spaces admit a nice structure of a complex manifold and even a structure of a Kähler manifold. And on the other hand, they are interesting in the higher Teichmüller theory. This is a theory that studies surface group representations and detecting some nice connected components in the space of representations of the fundamental group of a surface. Yeah, and today I'll give you some new insight into the structure theory of the of Hermitian Lie groups of tube type, and we will see how these groups can be realized as SP2 over non-commutative algebras. But before I start, I want to remind you some definition from the classical theory of symmetric spaces. So we consider smooth manifold, which is complex. So a complex connected manifold with a Hermitian metric M. And this manifold is called Hermitian symmetric space if for every point P in M, there is, so every point P in M is an isolated fixed point of an involutive holomorphic isometry on M. And the fact from the theory of, in fact, this is for Riemannian, for more general class of symmetric spaces, but it also holds for Hermitian symmetric spaces, that every Riemannian symmetric space, simply connected, can be decomposed as a product in symmetric spaces of 3 different types, M plus, M0, and M minus. M plus is always a symmetric space which is compact, and it always have a non-negative curvature. M0 is always isomorphic or isometric to a Euclidean plane, so to C to some power. And M minus is a non-compact type. It means that the curvature is non-positive, but not identically 0. And the canonical examples of these 3 types is a sphere is a compact manifold. And it, of course, it has this property that you essentially, it's symmetric enough so that you have this holomorphic isometry. So M0 is C or some power of C, and M minus is a hyperbolic plane. This is a complex manifold of curvature minus. And this example we will see later in more detail. And there is a theorem of Harris and Chandra that says that every Hermitian symmetric space, so actually, yeah, for a Hermitian symmetric space, it is of non-compact type if and only if it is biholomorphic to an open bounded symmetric domain. So we'll have an example of this. And a Hermitian symmetric space is called of tube type if it is a biholomorphic to a domain of the following form: V plus I omega, where V is a real vector space and omega is an open cone inside V, which is convex and which is proper in the sense that it doesn't contain lines. So, and yeah, and actually also the fact is that every Hermitian space of tube type is Hermitian symmetric space of non-compact type. And the example here is, as I said, a hyperbolic plane. So we know two classical models of hyperbolic plane. One of them is the Poincare disk, which is bounded, as you can see, the disk in C. And the upper half plane model, this is the tube domain. This is a real vector space, R, and an open proper convex cone inside R. This is R plus. This is the positive real numbers. Okay, so this is the example. And a Lie group connected, non-compact, semisimple, is with finite center and with K maximal compact subgroup. Then this group G is called Hermitian Lie group if the corresponding symmetric space is Hermitian. So for example, as we have seen, so the group of isometries of the hyperbolic plane is PSL to R. This group is Hermitian. And it is called Hermitian of tube type if the corresponding symmetric space of Hermitian is Hermitian of tube type. And in fact, Hermitian Lie groups and Hermitian Lie groups of tube type, they are classified, and up to coverings, they are SP2 and R for all n, SU and N for all n, SO star for n. So this SO star, this is some real form of SO for NC of the complex group, and it acts on some quaternionic vector space on H to the power 2n, which preserves some quaternionic skew symmetric form. So I'm not going to go deeply to the details about this group, but yeah. And then there's two other groups. This is SO2n, the zero component, the component of the identity, and the exceptional group E7, the right real form. Okay. Okay. So other questions about Hermitian Lie groups and Hermitian symmetric spaces? Okay, if not, then we can go to the motivated examples. So let's consider a matrix M, which is the matrix 2n by 2n, real. We can always write this matrix as 2 by 2 matrix, so that all the entries are matrices n by n. And this space of n, so it's algebra of n by n matrices is called A. And then this matrix M is symplectic if and only if the following property hold. So this is just the standard property. So this matrix 0 in minus in 0, this is the standard symplectic form. And here we just write the transpose matrix, the matrix itself, and then it should preserve this form. This is the condition to be symplectic for a matrix. So in some sense, you can see that this condition is very similar to be symplectic 2 by 2. So we can see, say that this matrix is kind of SP2, but over this algebra A. Another example, we can do completely the same, but for complex matrices. Yeah, we write everything here as before, but in this case, you see that we have so our group is sp2 and C, which is not Hermitian. Okay, and then we can do the third example. So we can again take the same algebra of matrices, complex matrices, but we can take the group U and N, which is Hermitian as we had seen before. And then we can write again this condition to be in this group. So this group preserves some Hermitian form of signature NN, and this is an example of such a form, Hermitian signature NN. You see the condition is quite similar, and moreover, this I, this is a central element, so we can actually cancel it, and we have essentially the same condition. There's again some kind of sp2, but you see that instead of just transposition, we use this transposition and complex conjugation. So this is also a symplectic group, but with respect to another, we call it anti-involution. So anti-involution, in this case, this is transposition composed with complete conjugation. The anti means that essentially that this involution permutes and exchanges the factors if you take like products of elements. Okay, and you can ask, why do we have such different properties? So sometimes it is Hermitian, sometimes not. So in the first example, we can take our algebra A, matrices, real matrices. Then our anti-involution is the transposition. Then we can take the fixed point set of this anti-involution in A. So these are symmetric matrices and by N. And then you can recognize a nice open proper convex exponent side, the space of symmetric positive definite matrices. In this case, we have a Hermitian Lie group sp2a. If we take the second case, we had matrices n by n complex, and again the same anti-involution, the transposition. Then we can take the fixed point set. These are symmetric n by n complex matrices. Actually, there is no nice open proper convex exponent side like this. And if we take the third example, we have again this matrices n by n complex. Then we have another anti-involution. Then the fixed point set is also different. These are Hermitian matrices and by n, and inside the space of Hermitian matrices, we have a nice proper convex cone of Hermitian positive definite matrices. So, in some sense, Hermitian case corresponds to existence of some nice proper convex cone inside the symmetric part of the algebra. And now we are going to do it more rigorously. So let's consider a unital associative algebra, semisimple. Semisimple is actually not very important at this point. It will be important when we construct models of symmetric spaces. But at this point, it's just some additional assumption. So real algebra, then we assume that there is an anti-involution of this algebra. This is the real linear map, which is an anti-involution. We square this map is just identity, and then it permutes factors. So the example will be like A is space of matrices, and the sigma is transposition together with the complex conjugation. Okay, and then the algebra A sigma, the involutive algebra, this pair, is called Hermitian if this subspace A sigma plus, these are essentially sigma A, so these are kind of squares. You can think on squares if you see this. Sigma AA, you can see that these elements are always sigma symmetric, so they are preserved by sigma. So then this subspace of A sigma is an open proper convex cone. And then this is just to fix the notation. We can take a topological closure of this space inside A sigma. and yeah, we denote it by A sigma non-negative. Okay, and then we can see that actually, yeah, we can consider the space A square as the space of column vectors, like here.
Женя, I'm sorry,
And
I missed the important thing. A here is always non-commutative algebra.
Not necessarily non-commutative, but this is a real algebra.
Okay.
Real algebra with an anti-involution like this.
Okay.
Yeah, the canonical example you can think on real matrices with the transposition.
Okay.
Okay, and then so we can consider the space A square and consider it as a right A model. So we allow to multiply by elements of A from the right. And then matrices 2 by 2 over A act on this space just by matrix multiplication. And we can consider the following A-valued form, which takes two elements of A squared and gives us an element of A, which is defined like this. We call this form the standard symplectic form. This omega is this, yeah, this is really kind of standard anti-symmetric matrix. Yeah, since the algebra is unital, so we have this one in A. So this is really a well-defined object. And then we can consider a subgroup inside the group of all invertible matrices 2 by 2 over A, sp2a sigma, which is the group of isometries of this omega. More explicit, it is just these are just all the matrices 2 by 2 over A, which satisfy the following condition. This is exactly the same. It's like completely classical thing, but just over non-commutative. And the fact which we proved is that this algebra A sigma is Hermitian if and only if the group sp2 A sigma is Hermitian of type. Actually, I will give you now the idea of this proof just by constructing models of symmetric spaces, and we will see explicitly this tube domain, which we discussed in the first part of my talk. Okay, models. So again, as before, we take our Hermitian algebra, and we can take the complexification of this algebra, just the standard complexification. Then we can consider the upper half space. By definition, this is the space of all, so the set of all elements in AC in the complexification such that the real part of this element is symmetric and the imaginary part of the element is symmetric positive definition. So you can really recognize here the generalization of the hyperbolic upper half space, upper half plane model. So this is R, this is R, this is R positive.
Женя, what is the positive definite part of the algebra A?
Here it is. This is the definition of the positive part. And this is for Hermitian algebras. This part is always an open proper convex. Okay? Yeah, you can again think on this our canonical example. So this A sigma is the space of symmetric matrices. This A sigma plus is the space of symmetric positive definite matrices.
Is there a completely positive version relevant to your study?
What do you mean completely positive?
Completely positive matrices.
Totally positive matrices.
Totally positive.
Yes, this is a weaker condition because the positive definite matrix is not positive, But every positive matrix which is symmetric is positive definition. Yes, I will give you later some relation to the positivity and to cluster algebras. Yeah, okay. And if in our examples, when A is the space of matrices, real matrices, this is the well-known Siegel upper half space, which is known as a model of the symmetric space for the group sp2.5. And our theorem says that the group sp2 A sigma acts transitively on U via Möbius transformations, I mean generalized Möbius transformation, like this. And the stabilizer of any point in U is a maximal compact subgroup of sp2 A sigma. So that means essentially that the space is a model of the symmetric space. So that it is in this case it is diffeomorphic to the symmetric, but in fact it is isomorphic as a as Hermitian symmetric space. Okay, and then you can also see immediately that this space is a symplectic, is complex manifold, because you see that this is a open domain inside A sigma C. In some complex vector space, an open subspace, so this is a complex one. Okay, and to see the bounded model, which we discussed before, we first need to extend our anti-involution to AC. So there are two canonical ways to do this once. We can do it in a complex linear way, like this, and we can do it also in the complex antilinear, like this. So just change the sign here. And then the fact is that if A sigma is Hermitian, then AC sigma C bar, this complex linear extension, is also Hermitian. But AC sigma C is never Hermitian. Okay, and then we can define the bounded model, which is the space of all Z inside AC sigma C in this with respect to the first extension of the anti-involution, and then this expression 1 minus ZZ bar is inside the symmetric positive part with respect to the second extension. So this, as I said, this algebra is always Hermitian, so the positive part is well defined. And you can also see that this domain is complex manifold, is a complex manifold, because this is an open domain inside this AC sigma C. And moreover, you can see that this is really a generalization of a disk. If A is just R, then here what we can see that means that 1 minus the absolute value of Z is positive. Yeah, this is the definition of the disk. And again, we have the similar theorem that says that the group, but not actually the group sp2A sigma, but the conjugate. We need to conjugate this group by this complex matrix. So this group is actually a group inside the matrices 2 by 2, but over AC. And this group is acting transitively on this bounded on this domain B. Again, via Möbius transformation as before, and the stabilizer of a point is a maximal compact subgroup of G, and that means that this is a model of symmetric space of sp2 A sigma. And actually, this transformation T is also known in the hyperbolic geometry. This is so-called Cayley transform. And now you can ask why actually this space, this B, is called bounded, because actually I didn't define any metric on them, on this domain. But actually it is bounded in the sense of Heine-Borel. That means that if you take the closure of this domain in AC sigma C, then it is compact. in contrast to the tube domain. If you take the closure, it is never compact because essentially you can go to the infinity in AC. Okay, good, but actually there is a natural metric P which makes it to a Riemannian or general to Hermitian manifold. Okay, good. Then yes, then we can actually study the boundary. Yeah, because P is pre-compact, so the closure is compact. So the boundary is a compact space. And actually, G has a nice action on the boundary. More precisely, so if we take the compactification, so the closure of B, it is compact, and G acts on, okay, it should be B bar, should be the compactification closure. And this action is, of course, non-transitive, because we know that the action is transitive on B and not on B bar. But there is a nice orbit inside B bar, which is called Shilov boundary. This is the unique closed orbit under this action. And more precisely, we can recognize this subspace inside B bar. This is the most degenerate part of this. So this you can think again that these are kind of matrices, but not positive definite, they are not negative. And there is a rank of this matrix. And the most degenerate somehow matrix, which is non-negatively definite, is 0. So this is precisely this part of the boundary. And here, the action of B is very interesting. First of all, it is transitive, as check. And this Shilov boundary, we can identify it with the space of so-called isotropic A lines. So these are all spans of, let's say, generic enough elements. The spans, or I mean, we take an element, we multiply it by all the elements of A, and then we have some subvector space inside A squared. But we assume that this space must be isomorphic as right A module to A itself. So that means in our example, that means this A, this is like 2n times n matrix, and this matrix has a full rank. Okay, and yeah, and it should be isotropic with respect to our form omega. And again, for our example, if A is equal to real matrices, this space of isotropic line can be identified with the Lagrangian Grassmann, with the space of all subspaces of R to N of dimension n, such that the symplectic form vanishes on this subspace. And actually here on this space, there is a nice positive structure. Namely, you can define the positive locus here. Somehow, if you fix two standard, or it can be seen in different ways. So you can take two standard isotropic lines. One of them is spanned by the vector 1, 0. The second is spanned by the vector 0, 1. And you can take all the lines that are transverse with respect to these two lines. Transverse means that they are in the direct sum. And in this space of transverse A lines, with respect to these two standard lines, so this space is disconnected. And there is one nice connected component, which essentially corresponds to the, somehow can be identified as a positive locus, as a positive subspace of this space of isotropic A lines. essentially that means that they can be parameterized somehow by this positive part of the of our algebra A. And moreover, if we have a configuration of n isotropic lines, then we can parameterize them by elements of A sigma. And this is the generalization of this well-known SL2R for contour of coordinates. So essentially, what you can think about kind of points on the disk that are mapped to the space of isotropic A lines, and then you can parameterize this configuration of isotropic N lines up to action of the group sp2ac. And then these coordinates are essentially the elements of A sigma. And then if all these coordinates are in A sigma positive, then this configuration of A lines is positive. And moreover, if you somehow take a triangulation and you change the triangulation, so you can so essentially what you have to, if you have a point on the circle, then essentially this is a polygon. Now you can triangulate this polygon, and essentially to any edge, internal edge of the triangulation, you can associate this element of A sigma. And if you change the triangulation, if you take a quadrilateral, then you replace one diagonal by the other one, then this change of coordinates is positive. It is essentially similar transformation as we have in the classical commutative cluster algebra. And this transformation, of course, preserves this positive locus. So, in fact, what the only thing I wanted to emphasize here that there is a nice non-commutative like cluster structure which was studied. I mean, not completely this structure, but in general was studied by Vladimir Retakh and Arkady Berenstein in their paper on non-commutative surfaces. And in fact, this provides an.
You mean the cluster structure on the non-commutative Grassmannian 2n?
Yes, kind of.
Okay. But it's simply.
But not Grassmannian, Lagrangian Grassmannian. I mean, this isotropic. So on this Grassmannian.
Lagrangian Grassmannian, isotropic Grassmannian 2n.
Exactly.
Okay.
And this provides somehow the geometric realization of this cluster algebra, which Berenstein and Retakh introduced in their paper. Because this theory they discovered in this paper, it's completely algebraic. And here we can really see this geometric interpretation from the one point of view, and then we can use this to understand representation of surface group into sp2a sigma and see this positive. So there's also some positive locus inside. We can really understand this positive locus using this algebraic construction provided by Berenstein.
Okay. I'm some confusion, however. So your symplectic structure is on the two-dimensional non-commutative space, but this structure of the Grassmannian of the isotropic Grassmannian, it is mostly on the n-dimensional space. The symplectic structure is on the n-dimensional. So the roles of coordinates changed.
This structure is on the space the space which is a configuration of this isotropic A lines. So this is not completely on this space of isotropic lines. This is you take several lines and you consider them up to this up to action of sp2a sigma.
Okay. Thank you.
Okay, good. Now, okay, and another interesting object which we could describe in our language, in our SP2A sigma language, is also, so we can also describe models of the symmetric space, but for the complexified. As I already mentioned, that this group, the complexified algebra with the complex linear extension of this anti-involution sigma, it is always non-Hermitian. It's never Hermitian. So this group SP2A sigma is never Hermitian. It's even it's never Hermitian. But we still can describe the symmetric space corresponding to this group in our terms. But for this, we need to go from complexification to quaternionification. So we take our Hermitian algebra A sigma, and we take the quaternionic extension of this algebra. So we take the tensor product with the quaternionic skew field. Inside this quaternionified algebra, we can recognize the copy. So there are several copies, actually infinitely many copies of AC. And we fix this copy. That means that we take the copy which is generated by the imaginary unit I. And again, we can extend our anti-involution sigma to AH. So there are several ways, but there are two ways that are particularly interesting for us. One of them is kind of quaternionically linear. Like this, we use sigma c in the first coordinate and sigma c bar in the second. Okay, I need to say that every element in AH can be written as Z1 plus Z2 times J, and this Z1, Z2 are in this particular copy of AC inside the quaternionic extension. Okay, and then we can also extend it differently. Namely, we can take, this is kind of quaternionically antilinear extension. So we take the sigma c bar in the first component and then sigma c in the second component. And then there is again the similar proposition that we had for complexified algebra, that's AH sigma 1 is always Hermitian and AH sigma 0 is never. Okay, good. And then we can again define quaternionic upper half space is very similar. Namely, we take this element Z1 plus Z2J in the AH sigma 0, symmetric with respect to the first extension. And then we require that the second coordinate in the positive locus, but with respect to, because this is the complex, this is an element, the complex algebra. So we need to require that it's positive with respect to the second extension of the anti-involution, but for the complex algebra. So it is well defined because this algebra is Hermitian. And again, we have the similar theorem that the complexified group acts on this space transitively with compact stabilizer of every point and maximal compact. So that means that this is the model of the symmetric space. This is not a Hermitian symmetric space. This is, so you can actually see, I mean, probably not directly from this description, but you can see that this space is not an open domain in any complex vector space. So in fact, this is a generalization of well-known model of the hyperbolic tree space, which is three-dimensional. It has no chance to be complex, manifold. And then we can also define a quaternionic bounded, which is so quite similar to the previous one, that are all the elements in AH sigma 0 which satisfy this relation. So the sigma 1 is again this anti-involution which makes our quaternified algebra Hermitian, and yes, and therefore this positive locus is defined. And there's again the similar theory that some conjugated group acts here, and it is the action is transitive, and that stabilizer of a point is maximal compact. So this is. And again, we can study the boundary here. This is kind of similar, and there is also the a closed orbit like this, kind of Shilov-like boundary, but I mean, it wasn't known in the theory of Lie algebras. And actually, yes, it can be again identified with the space of isotropic, but now AC lines. And unfortunately, on this space, there's no nice positive structure. So I think there's no positive structure at all on this space. So essentially, that means that if you can take a triple of isotropic, pairwise isotropic lines, that the action is transitive. There is no positive locus inside. Okay, and to summarize and to finish my talk, I would like to show you which group we can realize and which not. So we have the following algebra. So the first one is our main example, real matrices with transposition. So we can realize this real symplectic group, and we can realize the complex symplectic group. If we take the matrices, complex matrices with anti-involution and the complex conjugation, then we can realize U and N that we also have seen today, and its complexification is GLN 2C. Okay, then we can also take the quaternionic matrices and pen with the anti-involution, which is transposition, and the quaternionic conjugation. Then we can realize this quaternionic group SO star, whose complexification is SO4N. And then there is one more interesting example, which is the Clifford algebra. Clifford algebra, which comes from some vector space with a bilinear form, and we require that the bilinear form had this particular signature 1n. And there is some appropriate anti-involution on this Clifford algebra, and in this way we can realize this SO0, this indefinite orthogonal group. But unfortunately, this construction cannot be done for the complexification, because actually this group is not really the group sp2a sigma, but this group is some nice subgroup inside sp2a sigma. So this group is slightly more difficult than these other three families. This is why the complexification doesn't work. And the only group which we are not able to realize so far as sp2 over something is this exceptional. And the reason, actually, we understand precisely why we cannot this, because the corresponding AC, the object which must be A sigma, this symmetric domain, this symmetric subspace of A, is the space of octonionic 3×3 matrices. And there is a positive, the notion of positivity, and there's the positive subspace of octonionic 3×3 positive definite matrices. And the problem is that there is a result that says that we cannot embed this octonionic 3×3 symmetric matrices nicely in any algebra, in any associative unital algebra. So there is no associative unital algebra which contains this particular 3×3 octonionic symmetric matrices as the symmetric part. So there's no way to realize it precisely like this, but we conjecture that probably we can relax some condition for the algebra. Probably it shouldn't be the algebra, but probably some object which is algebra-like. Maybe this should be kind of monoid. So there should be some. So for example, there's no sum inside this object, or some maybe the multiplication shouldn't satisfy all the properties of the multiplication in the algebra, because actually we know how the model of the symmetric space looks like for this group. So we know many things about this group, but the only thing we cannot do, we cannot realize it as sp2c. Okay, let me stop here, and then we can discuss your question if you have.
Thank you very much. So my principal question is about the higher dimensional generalization. So is it natural to consider the SPN?
Yes, of course, it's possible. But the problem is that in these groups there are no nice positive structure. So our goal was to start, because this Hermitian Lie groups of tube type, they have this nice structure, this nice positive structure on the space of Lagrangian. So for SP2 and R, they have this nice positive structure on the Lagrangian Grassmannian, which gives rise to some nice positive representations of the surface group. And yeah, because I come from this part of the story, from this geometric part, from the representation part. But for any other n, there's no positive structure. The groups are, in this sense, they are probably one can ask some interesting question about them. But in general, of course, you can define in the completely the same way the symplectic or the orthogonal group, like n by n over A, and all these objects are well defined.
Okay. Just the stupid question. So why it is interesting to find such a realization of symmetric spaces as in terms of this non-commutative groups?
Because in fact, it is much easier from geometric point of view to work with this model. Because in general, the symmetric space is just G mod K, group G mod the maximal compound. And if you have some nice geometric realization, you can really understand what are geodesics in this space, what are horospheres, horocycles, whatever. You can really understand the geometry more in detail. For example, this is why the Siegel upper half space was introduced, because it was a nice model for the symmetric space of the symplectic group. And we just generalized this for larger class.
Is it suitable for studying some integrable systems, some dynamics on symmetric spaces?
Yes, I think so. What the story that I know the story about this pentagram maps.
Yeah.
And actually, you can define. So you know how this. So you somehow take the points in the projective plane, you connect it by lines, and then you take like short diagonals, and then you can go on. And then you can parameterize them using some coordinates. You can find some integrals, and I mean, yeah, this is very nice. And there is a generalization of this pentagram map, which was developed by Tamonov, Shapiro, House, if I'm not mistaken. They do completely the same story, but they take like the space of dimension 3n, and they consider inside the spaces of dimension n. And essentially, they do precisely the same. And then they can also parameterize them using some non-commutative cluster-like coordinates, which are very, very similar to the coordinates that we have here. And also, there is some non-commutative Poisson structure on this dynamical system. And essentially, what we can do exactly the same. We can just replace R to 3n by our algebra A to the power 3. And we can go on. And there is some interesting dynamical system that can be parameterized by elements of A.
Okay.
And if the algebra is Hermitian, then I suppose there is some positive somehow in the moduli space of this pentagram dynamical system. There is some positive. Okay, so I'm not really an expert in this theory, but I suppose that there is something interesting.
Perfect. Zheng, thank you once again. It was very interesting.
Yeah. It was a pleasure to give. Thank you very much for the invitation.
Thank you. We stop here. Thank you. Bye.